end with special relativity, because we are not here to discuss special relativity, but since gravity grew out of special relativity, we had to have a fairly coherent picture of it. So what we saw, that we can classify matter by mass and spin. On the other hand, we can define conserved tensors, spin, and the non-conserved spin angular momentum tensor, but together with the orbital angular momentum it is conserved. So the energy momentum is partial k, t, I, k is equal to 0, and the spin angular, the conservation of total angular momentum is divergence k, s, I, j, k minus t, I, j, anti-symmetric is equal to 0. These are the neutral laws. For inner groups, we will later, or interior groups or inner groups, like U1 in electromagnetism or SU2 and what have you, we can also apply the neutral theorem, but then only the second piece, which contains the variation of the field, contributes, whereas the variation of x doesn't contribute because the inner transformation is always made at the same point. So it's a specific thing for the Poincaré group that it touches this first term and gives the contribution to the energy momentum tensor. I always tell my students, there are many people who didn't believe in special relativity up to 30s or 40s, but one of the predictions of four-dimensional special relativity is the energy mass equivalence, and at the latest, at the experiment or nuclear experiment in Alumoporto, (1945). This corresponds to energy mass or mass transformation into energy at a large scale, and nobody could doubt anymore that this mass energy equivalence even can show it that it's order of magnitude correct in this experiment, that this is a fact of physics. So this is the Big Bang at the end, which proved special relativity beyond reasonable doubt. Now in section 1.5, I want to start with the equivalence principle. Equivalence principle and gravitation. Gravitation. So what it turned out that Newton's theory of gravity, as you know, is action of distance theory, and it fulfills field theoretical formulation of Poisson equation with the right-hand side is the density. And the Poisson equation has, of course, the Laplace operator, which is only space-dependent, it's not relativistic invariant. So what you could do is to make it a wave operator that people have tried, but that didn't succeed because the mass density is just not the source of gravity according to our present wisdom. So mainly two names come to Nordström, Finnish physicist, and Abraham, German physicist. They are before after 1905, partly even before special relativity was played, they looked into this question, And for instance, Nordström proposed a theory which I think also Levi inquired into, which didn't predict the deflection of light, for instance, which was not known at the time anyways, but this led to no success. So Einstein made a new beginning, 1907, and formulated this equivalence principle. Shortly put, it's just saying that if you go in an inertial frame, and if you go from an inertial frame in an accelerated frame, you can simulate gravity. It looks like a gravity field for the reason that of the equality of inertial and gravitational mass. So it's an equivalence between one situation, which is just an acceleration, and another situation where you have no acceleration by the gravitational field. And these two situations you can compare. So it's also at the same time a recipe for doing calculations in gravity. If you don't know how gravity is described, you just do the calculations in an accelerated frame, and if you then are clever enough, you can conclude how the corresponding gravitational effects look like. Okay. So the experimental basis were the measurements of Friedrich, a Hungarian physicist. I mean, they were finally published 1922, but he started to make experiments 1800 and something, I don't even know exactly when he started. And they were finally published, but they were known to Einstein and other people in the trade very well. So that's equality, that the inertial mass, which appears in Newton's equation of motion, mass equal force equal mass times acceleration, is the inertial mass, and then you have the gravitational mass. This is the mass in Newton's attraction law, mass 1 times mass 2 divided by r squared. The distance between both masses is proportional to the force, the gravitational force. And it turned out, and nobody knew why, in suitable units, they are always equal. And this equality was not understood by anybody, but nobody cared, apparently. So Einstein, I quote Einstein, with the equivalence principle, we are able to produce a gravitational field merely by changing the system of coordinates. I don't have to write it out, I read it again. That's a quotation from Meaning of Relativity, which was translated into English, Princeton University Press, 1921. We are able to produce a gravitational field merely by changing the system of coordinates. So you can produce a gravitational field, but only a very specific gravitational field, a homogeneous gravitational field. And Einstein used always very nice pictures, and I use now Einstein's elevator, I call it Einstein's laboratory. Einstein's laboratory. Later in gauge theory, I will have Kibble's laboratory. So I have two laboratories. Now we have a laboratory which sort of tries to collect all the arguments which Einstein had for general relativity. Later we will have a laboratory of Professor Kibble out of London, and I call it Kibble's laboratory, where you have, well, similar like Einstein lived, but some the basic difference is here we have mass points, and later we will have electron fields described by a Dirac field. That is the main difference. So the equipment and the constructs in Einstein's theory laboratory, the equipment and the constructs which we are using in Einstein's laboratory. So you assume you have such an Einstein laboratory somewhere in the basement, you have some laboratories, we could have an Einstein laboratory. What do you have? You have a neutral point particle, with mass m. You see, I don't say with inertial mass or with gravitational mass, because we know by experiment they are the same. Second, an inertial frame, which in your laboratory downstairs it would not be an inertial frame because it moves on the Earth with respect to solar system moves with respect to the galaxy, etc., etc. But we know how to define it, such a frame, an inertial system, an inertial frame, K, and third, now an accelerated i.e. that is a non-inertial frame K' prime, and well, somewhere we get a homogeneous gravitational field. And fifth, we have light rays at our command. Let me make a remark to each of it. Okay, first of all, I mean, we have a neutral point particle. This is a big word, but it is not so easy to really define. I mean, a point particle, it should be structureless, like a point. It should be spherically symmetric. No electric charge, no magnetic moments, no spin. It's not so easy to find such a particle, but we are optimistic that at least macroscopically we can do something like that. But of course we should be aware that even a planet could be a point particle later if we do calculations in general relativity. But it could be also a very small particle, a minute particle. So the particle concept is a kind of abstraction of the center of mass motion of an extended object, of course. But with these abstractions, one always works in these Gedanken experiments which Einstein liked so much. Well, and this is now also in number 2 is also a difference which comes in to gauge theories. Einstein, for Einstein, inertial frame, not from frame, an inertial frame K is just a system of coordinates. And in his case, a system of Cartesian coordinates, right? It just takes here Cartesian coordinates, which he, in his original work, had a capital XI. So, for Einstein, a reference frame is a coordinate system. In mathematical language, a holonomic system. And this is the difference to a frame if we describe an electron wave field, we need a Vierbein tetrad or a co-frame, whatever name you prefer. And you refer your Dirac wave field to such a frame. And so a frame in later in gauge theory will always be a co-frame in the mathematical sense. Whereas a frame in Einstein's context is always just a coordinate system. You have Cartesian coordinates, you go in a curvilinear coordinate system, it's already a different reference frame. And the reference frame, even in his language, he doesn't make a difference between curvilinear coordinates and reference frames. This is for him the same. Right? And this is only I contend that this is only true and correct for point particles, but it's not correct for electron fields. So you cannot apply an electron in such an Einstein laboratory. It sort of is beyond the Einstein laboratory. This is one of the points which will turn out to be very important. Okay, and number 3, an accelerated frame. You just go to curvilinear coordinates, and you can. And the metric is then, of course, no longer diagonal. Then you have a dA square, quite generally, Gij dxi times dxj. This is the metric, and you can, which was depends on x in general. It is no longer constant like in Minkowski space-time in Cartesian coordinates. It is symmetric. Tensor field with 10 independent components because it's symmetric in 4 dimensions with tensor, symmetric tensor. It's a matrix, 4 times 4, it's symmetric, and it has 10 independent components. Now, there is also a thing which plays a role later in discussions, perhaps not for us, but in physics it's important. An acceleration has always linked with it length parameter. So it's not dimensionless. So if you have an acceleration, so I call it the translational length parameter. Which is L translation by definition c square, velocity of light square, divided by a, which you can, this time my dimensions are correct. Now, for instance, and I stress translational because there is also a rotational length parameter, which is also well determined. So if you have an acceleration, you can always say how big this translation. Well, for instance, acceleration on the Earth, this L translation is c square divided by the g on the Earth, gravitational acceleration of the Earth. If you do your calculations, it turns out to be 10 to the 16 meters. That's about 1 meter. So if you have an Einstein laboratory on the Earth with a few meters in diameter, it is well beyond this critical length. Only if you had very, very high accelerations, you would have to rethink these things Einstein did. And this is a limit where the equivalence principle can break down if you go to such high accelerations. And that is often the case even in some approaches to quantum gravity, which imply accelerations which are much higher than this critical translational acceleration. But still people take general relativity, which is based on the equivalence principle, which is a contradiction, of course.
I guess maybe a comment. So this numerical negative are quite different from laboratory. So actually, in the argument of Einstein in his 1907, yes. 1908 paper, he actually really used infinitesimal space
yes, yes.
to argue it is homogeneous.
Yes.
But if you use if you take acceleration frame with special relativity, you will not get homogeneous fields. Okay. So let's just comment. But it's not picky. It's just say if you want to actually.
No, it's not picky because this is going on in recent discussions. I mean, there is nothing like a homogeneous gravitational field, period. Because if it were homogeneous, the curvature tensor vanishes, then gravity is absent. So there is nothing, and so it can only be some approximation. And Einstein was clever enough to find just this approximation which is good enough for deriving his theory. But as a matter of principle, one has to be very careful. You have always to compare how well the connection with respect to the curvature, whether this is a small quantity or not.
Right, but even if there's no curvature, if you strictly to accelerating frame, then you will not get homogeneous field.
Yes.
Okay.
Yes.
Okay.
Yes, that's clear. Okay, I could extend on that, and that's really an important question, which also plays a role in present discussions, so that, as we will see soon, the gravitational field is described by the Christoffel symbols, which we denote here by gamma-Twiddle. And the kernel of the Christoffel symbol is a field strength, which is called the Riemann tensor, R-Twiddle, which is the curl. I should write a capital C because it's a four-dimensional curl. The curl of gamma, and only if gamma-Twiddle over R-Twiddle is small. If the d is small, the dimension of our experiment is small. Against that, we can trust that the gravitational field is sufficiently homogeneous. Okay, section 1.6. Force-free motion of a point mass. Force-free motion of a point mass. Christoffel symbols. Christoffel was a mathematician, German mathematician, who published this stuff around 1870 or something. Christoffel was the mathematician who put a lot of the Riemannian geometry on a formula basis. Even the curvature tensor was really written out explicitly by Christoffel. So originally it was called Riemann Christoffel tensor. That was too long. Forgot him. I think we had it. So we go in our Einstein laboratory. We go into K in the inertial frame with the capital coordinates. ds, as is the ds square is the line element, and here we have the acceleration is equal to 0. We have our mass point, and it moves acceleration free. And now we go to curvilinear coordinates. The coordinate transformations is as usual. We have dxi is partial dxi with respect to small x k times dxk, and we just introduce this into this equation. We spell it out and make this transformation. Then you find that d2 is small xi over ds square. ds is a line element. Plus the so-called Christoffel symbols, gamma-Twiddle, jki times dxj over ds times dxk over ds is equal to 0. So this is the same equation. This is just written in new coordinates. Very nice representation of these ideas is given by Schrödinger, one of my favorite books, Schrödinger Space-Time Structure. I recommend this to any student who is interested in relativity. Should read this book. Cambridge or something, 52. And these Stoffel symbols are now defined just in terms of the derivatives of the metric. So we have here Sciama-Kibble. How did I define it here? Is JKI is by definition 1/2 J by L times partial J GK L plus partial K GJL minus partial L times BGJK. So you can easily see that this expression is symmetric in J and K, and this is also symmetric in J and K. So the whole, so you can memorize the index position by knowing that it's symmetric in J and K in these indices, and here is also symmetric. So the whole Stoffel symbol is symmetric, and this is important because later in gauge theories we will meet quantities which in special cases become the Stoffel symbols, but which are not symmetric. Which of course is wrong. I should write Kj. So it has, this is symmetric tensor 10 times 4, 40 independent components. Pretty complicated gravitational field, isn't it? 40 instead of 1 potential in Newton's theory. But on the other hand, these 40 independent components can be derived from the metric. The metric has 10 independent components, so that looks better.